Welcome to lecture number 2 on complex analysis, which is MSM 341. So we are going to start the class. Remember last time we looked at lecture number 1, in which we're talking about the basic definitions and some basic properties of complex numbers, or rather some algebraic operations on complex numbers. Now today we are going to look at lecture number 2. This lecture comprises of the complex plane or Argand diagram. Then we are also going to look at the modulus and argument of a complex number. So these are the components that you are going to look at. So we are going to start with the complex plane. Now, for example, if we recall what we said about the complex number, by definition, a complex number is a number that can be written in the form x plus iy, where this I is representing the number, the square root of -1. So if you look at this complex number, you can identify it as a point in the R2 plane, or rather in the x or y plane. So you can identify it because from the way it has been written, you can identify it. You can put it in point form as x comma y. So which this x is representing the real part of the complex number z, and the y is representing the imaginary part of the complex number z. Now, since you can identify this complex number as a point in the R2 plane, which means this same complex number, you can also represent it graphically. You can represent it graphically as a point P. This point P, which is equal to x comma y. Remember, x is the x coordinate, is the real part of z, and y is the imaginary part of z. Now, if you look at the way it is in figure 1, this figure which is here, if you look at it, you see the y-axis, when you are in the complex plane, the y-axis represents the imaginary part of z. Then the x-axis represents the real part of z, if you look at it from the R2 plane. So now, this is how we represent the complex number. So every time you are reading a complex number in this plane, what you're supposed to read, you read the real part first, then you read the imaginary part. Just like the way we do it when you are representing a given point in the real plane. Now, if you look at the point O, remember the point, the origin. If we would want to write this, the coordinates that it has are 0, 0, because it's the origin, it's the starting point. And remember, the complex number 0, you can also write it as 0 plus I 0, 0 plus 0 times I, where I is the square root of -1, which still will give us equal to 0. So this point, which represents the complex number, the origin, or rather which is equal to 0, this one represents the complex number 0, which is equal to 0 plus I. So now, all the points on the x-axis and y-axis have coordinates of the form. So now, if you look at along this x-axis, every time we pick a point along this x-axis, remember that the y coordinate will be 0. The y ordinate will be 0, but the x coordinate will be given. So in that case now, if this complex number is along the x-axis, then we can represent it as x comma 0. It's the real part comma 0, because the imaginary part will be 0. Also along this y-axis, or rather the imaginary axis, the real ordinate, which is the x coordinate, in short, ordinate will be 0, but the y ordinate will be some value. That's why now we are saying in that sphere, we are going to represent it as a coordinate which is x, 0 and 0, y. Now, these coordinates, they correspond to complex numbers, like because you have a point like x, 0. So the real ordinate is given is non-zero, but the imaginary ordinate is 0. As such, we are going to write it as x plus I0, which is just the same x. And for the pure imaginary one, we are going to have 0 plus IY, which is equal to just IY. Now, so in this scenario, because what we are saying is along the x-axis, we represent the coordinates by x, 0, and along the y-axis, which is the imaginary axis, we represent them by 0, y. So for that reason, the x-axis and y-axis, we call them the real and imaginary axis, respectively. So this x-axis is the real axis of z, and the y-axis, we call it the imaginary axis of z, and we call any coordinates along this as the imaginaries, and any coordinate along this, we call them as the reals. Now, this same diagram, this same plane on which we represent the given complex number is called, we call it the complex plane or the Argument diagram. Now, since this complex number, any complex number, every or any complex number can be represented on the Argument diagram, then as a point, you can represent it on the Argument diagram as a point. So which means from where the complex number is, let's look at this previous diagram. If you look at this diagram, we have the point P, which is somewhere here. So now this point P, it started where? It started from the origin. So we can draw a line from the origin to where this point P, which is representing this complex number, is. So what I'm trying to say is that, so we can also, apart from representing a given complex number as a point, we can also represent it as a vector, as a given vector from the origin. Now, which is the vector OP, this vector OP also represents the given complex number with this directed line segment. This directed line segment, remember, directed line segment means in a specific direction. You represent this vector in a specific direction. Now, the starting point will always be the origin, and the ending point, which is the terminating point, will be the point P at which is representing that given complex number. Now, you see, because we are able to represent this complex number as a vector, then it's very possible for you to find the length of this complex number from the origin to where it is. It's very possible we should be able to find the length or the distance from the origin to where this complex number is, based on the fact that we are able to represent it as a vector, which we call the magnitude of the given vector. So the magnitude of this given vector is equal to the distance or the length of this complex number from the origin. And remember, as you were drawing this line made an angle with respect to the x-axis, or rather with respect to the real axis of this complex number. So this angle you see, the angle, let me just let's try to scroll it so that everything that I'm explaining is here. So because we are able to represent a given complex number as a vector, this means we should be able to find its length. This length, which we have abbreviated by R, we call it the modulus of a given complex number. The modulus of a given complex number. Now, this same complex number, as you're representing it as a vector, it makes an angle theta with respect to the real axis. It forms an angle in an anti-clockwise direction. So it will form an angle in an anti-clockwise direction with respect to the real axis. So this same angle that you've seen is the one that we call the argument of a given complex number. So the argument of a complex number is the angle that is formed by the complex number with respect to the positive real axis. And then the distance from the origin up to where the complex number is, that we call it the length of this complex number, which we call the modulus of a given complex number. Now, in the next part, we are going to look at how we can calculate this argument of a given complex number and the modulus of a given complex number. Now, if we need to look at it from the point of coordinate geometry, under coordinate geometry, you know, when you are finding the distance between two given points, we are using the modulus symbols to represent the length of a given point from another point or from the origin. So this is now which brings us now into this definition. So what I'm saying is the length R, which is equal to OP, is called the modulus or absolute value of a complex number Z, and is denoted by the module, which is with these symbols, which means modulus of the complex number Z. And this length, if you recall, so you can even, let me just take you back, you can even apply the Pythagoras theorem here. Remember, when you read the real ordinate and the imaginary ordinate, you can form a rectangular shape. You can form a rectangular, a right-angled rectangular shape. And by, if you look at, you know, the length from the origin to where the point P is the one that we have given it by R. And the length from along the real axis, the distance is X, and along the imaginary axis, the length is Y. Now, if you recall under Pythagoras theorem, that means it will be the square of R is equal to the square of the adjacent. The square of the hypotenuse is equal to the sum of the square of the adjacent. So that will mean the square of R is equal to the square of X plus the square of Y. So now in solving for R, we are going to have R is equal to the square root of the sum of the square of the real axis and the real ordinate and the imaginary ordinate, which is the one that is just written here. And also, you should also take note that the length of a given, the length is never negative, it's always positive. So you never find the length which is negative. So now we're saying the modulus of Z is just equal to the square root of the square of the real ordinate plus the Y, the square of the imaginary ordinate. Now this same angle theta, the angle theta, which in most cases we write it in radians, but you can also use degrees where possible. So this angle theta, which the given complex number makes with respect to the positive real axis, we call it the argument with a small letter a, argument or amplitude of the complex number Z. And in notation form, we use the symbol ARGZ, which means the argument of the complex number Z. Now, the issue here is how can we get this argument of a given complex number? How are we going to get the argument of a given complex number? So basically, if I can just take you back to this diagram, And in the scenario where you are given, this complex number has been given, remember, you should be able, in that complex number, you should be able to have the real part of that complex number and the imaginary part of the given complex number. So trigonometrically, from trigonometry, you should be able to find the angle theta by using the imaginary part of the given complex number and the real part of the complex number by taking the tangent of theta, which is equal to the opposite over the adjacent, and our adjacent is x, the opposite is y, and then you solve for your angle for the argument, which is theta. So this formula, which is the tangent of theta, which is equal to y over x, it should be able to help us to find the angle theta, of which to get it, we are going to take the arctan from both sides of this equation. So now, so the angle, we call it, this theta is called the argument of the complex number. Now, if you look at we also, under trigonometry, we looked at what we call quadrants. Under the quadrants, we have 4 quadrants. We have the first quadrant, third quadrant, the second quadrant, third, and the fourth quadrant. Now, it depends to where this complex number lies in. Is this complex number, does it lie in the first quadrant, or is it in the second quadrant, or is it in the third quadrant, or is it in the fourth quadrant? So where the complex number lies in, it also affects the argument of that given complex number. It also affects the argument of the given complex number. Now, you have a situation also where you find that you have this same argument, which we abbreviate by small a, this argument of a complex number. There is this argument which lies in the range. So the argument of a complex number, the values of theta, which is the argument of a given complex number, lying in the range from negative pi to pi. From negative pi to pi, we call such values, we call them the principal value of the argument. So how can you tell that this is the principal value? There is an argument and the principal value. Some authors use the word the principal argument. Now, when abbreviating it, also remember an argument. This one, it's not limited. It's not unique. It's a multiple of 2 pi, 2n pi I. This is a multiple. Now, this is the argument of a complex number. Now, the principal argument is very unique. This argument, it lies between negative pi and pi. What do we mean by lying between negative pi and pi? In short, it lies from 0 to negative pi, or from negative pi to 0, and also from 0 to pi. So your value, the principal argument of a given argument of a complex number, it lies either between 0 and negative pi, or from 0 to pi. So if now, let's look at this example number 1 though. If you look at some examples that involves the principal value. So if I see the principal value of 120, the principal value of 120 is 60 degrees. 60 degrees. Now, although this 120, though it's also, if you look at 120, though this one, I think there should be an error with this one. It's not supposed to be 120. Now let's go to part 2. Part 2, if you look at 240, the 240 is, if you look at it, is in which quadrant? If you look at this 240, sorry, just that I wish I could do. If maybe you can just type and tell me where this 240 lies. So this 240, is in the so the 240 is in the third quadrant. Now you look at the third quadrant. If it's in the third quadrant, that means the principal argument, which the principal value of this 240 degrees is the negative of 120 degrees. So, because remember, if you look at the quadrant, okay, let me just maybe take you back to this figure. So, if I'm going in the anti-clockwise direction, I'm going to start from 0. In the anti-clockwise direction, I'm counting the angles to be positive. So from 0 to 180. That is second and third, first and second quadrant, the principal argument will be positive. If the angle lies in the first and second quadrant, then the principal value of those angles is positive. You can think of any angle. You can think of an angle like, let me just give an example like 380. If you look at 380 as an example of that angle, if you look at 380, this angle lies in the first quadrant. This angle lies in the first quadrant. So 380 degrees lies in the first quadrant. As such, its principal argument is 20, a positive 20. That is the principal value of the angle 380. Now, if you look at the 240, this angle lies in the third quadrant. Now, the principal value is, so in this case now, we are also going to start from 0, but you move in the clockwise direction when you are reading the principal argument. So we move in the clockwise direction. That means the principal argument will be a negative. From 0, you move now from the positive real axis, in short, from the positive real axis, you start moving in the clockwise direction. So then the principal argument is going to be a negative. But if from the positive real axis, you start moving in the anti-clockwise direction up to 180. So the principal value of a given angle will be a positive value. Now, so this is where now you are seeing negative. Also, the principal value of 330 degrees. Remember, 330 degrees is this one is in the fourth quadrant. So the principal argument, the principal value of this angle is the negative of 30 degrees. Okay, now let's look at example number 2, which involves the modulus, on finding the modulus of a given function and also the argument of the given complex number. So we're going to look at the modulus of a given complex number and the argument of a given complex number. We have not said the principal value of the argument, but we are just saying the argument of a given complex number. So the first Roman number 1, you have 2 plus 2 times I square root of 3. Now we are going, if the other way around to handle such a question, because remember, you are going to find the argument of this complex number. Yeah, when you're finding the modulus, that's not an issue. You can just find it from there. But when you're finding the argument of this given complex number, the best thing you can do is first sketch this given complex number on the argument diagram. From there now, you are able to determine where this complex number lies. So you are able to find out where this given complex number lies, whether it lies in the first quadrant, second quadrant, third quadrant, or in the fourth quadrant. Now, if you look at our complex number, let's first start. What you're going to use in any case, both 1 and question number 2, we are going to use the formula, the modulus of z, which is equal to the square root of x squared plus y squared. This one will use it to find the modulus of this complex number, and the formula, the tan of theta, which is equal to the real part of a complex number divided by the imaginary, the imaginary part of a complex number divided by the real part of a complex number to find our argument. Now, if we let this given complex number in 1, which is 2 plus 2I times the square root of 3, we let it be to be z, then using this formula, we could see that comparing this to z, which is equal to x plus iy, our real part x is equal to 2, our imaginary part y is equal to 2 times the square root of 3. Now, let's look at this. If you look at the real part of this complex number and the imaginary part of this complex number, both are positive. All of them are positive. What does this mean? This means our complex number lies in the first quadrant, where both the real part and the imaginary part are positive. This means this complex number lies in the first quadrant, as you can see from this diagram. Remember, 2 times the square root of 3 is a number which is closer to, which is 3 point something. Okay, so now because the square root of 3 is 1.73, somewhere there, rounded off. So if you multiply that by 2, you get something like 3.464, which is just 3.5 as your imaginary part of the given complex number, which is just by rounding off to one decimal place to give us 3.5. So this point is a point P, which is equal to 2,3.5, somewhere there. So this is where your complex number is. Then now, from this now, you should be able to tell that our angle theta, the argument of this complex number must lie in the first quadrant. So doing so, now we need to find now the modulus of this given complex number. So the modulus of this given complex number is the square root of the square of the real part plus the square of the imaginary part of a given complex number. You don't include the imaginary number when you're squaring. Don't square the imaginary number, no, but square the imaginary part of the given complex number, of which the square of 2 is 4, the square of 2 times square root of 3 to give us a 12. Because the square of 2 is 4, then the square of the square root of 2 to give us 3, which is 4 times 3 to give us 12. Now when you add this to give us 16, and then the square root of 16 is 4. Now if you look at our modulus, it is positive 4. But if you look at from the quadratic point of view, we could have gotten plus or minus 4. But remember, the length or distance is never negative. As such, we just concentrate on the 4. Then for the argument, its argument theta is obtained by the argument of this complex number. We obtain it by taking the tan of theta, which is equal to now the imaginary part, which is 2 times square root of 3 over the real part, which will give us the square root of 3. Now, as such, from this, we are going to have the theta, which is equal to the arctan of the square root of 3, which will give us in degrees. This is equal to 60 degrees. If you go to special angles that you learned in first year, if you revisit special angles, you discover that this will give us 60 degrees. And in radians, this is pi over 3 radians. Then you are done. You have found the modulus of a given function, which is equal to 4, and the argument of this given complex number, which is the pi over 3 radians, or the 60 degrees. Now, if we also go to part number 2, the complex number itself is -1 minus 1. Now, this means if we let this be equal to z, which is equal to x plus iy, then the real part x is equal to -1, the imaginary part y is equal to also -1. As such, now if you look at it, both the real part and the imaginary part of this complex number are negative. Now, in which quadrant can we find both the x and the y being negative? This is in the third quadrant. So this is in the third quadrant, which means our angle theta will be an angle in the third quadrant, which this complex number has made with respect to the positive x-axis. Now, for that, the modulus of this given complex number is the square of -1 plus the square of -1. It will give us the square root of 2. And the angle phi, which this, the angle theta, which this the angle theta, which this complex number will make with respect to the x-axis when we solve, what you're going to get is a 225 degrees, which in radians is 5 pi over 4. You can compute that because we've been doing these things in the first year. So this is how we can find the argument, the modulus of a given complex number with respect to the formulas that we've learned. Now, the next piece of information, what this theorem is trying to tell us is on the relationship between the modulus of the given complex numbers and the argument of the given complex numbers, which relates to the product and the quotient. So this theorem is saying if we have two complex numbers z, which is equal to x plus iy, and w, which is equal to x plus iv, if these are the two complex numbers, then under multiplication, so here the modulus, if you take the modulus of the product of two complex numbers, so the modulus of the product of these two complex numbers, this is just equal to the moduli, this is equal to the product of their moduli. So we are saying the modulus of z times w, this is equal to the modulus of z times the modulus of w. And the argument of their product, this is equal to the sum of their argument. So the argument of z times w, this is equal to the argument of z plus the argument of w. Again, under division, so the modulus of the quotient of the two complex numbers, so if you take the modulus of the quotient of the two complex numbers, this is equal to the quotient of their moduli. This is equal to the quotient of their moduli. And the argument of the quotient of the two complex numbers, this is equal to the difference of their arguments, as you can see. So you can prove this, but the proof, I think maybe you did it some time back in first year, so we are just perusing through, and then this is just like an introduction to complex numbers, which our aim is to look at the other parts that involves the sequences, power series, that also going to look at analytic functions. So before we do that, that's why we started with this part of the module. Now, if let's go to example number 4. So in example number 4, I'll do part 1. So the other parts are already solved. So all you need is just to go through them. So what you're saying is, or maybe I can just, what you're saying is find the modulus and argument of each of the following complex numbers. Maybe if you look at the first one is z is equal to 1 plus I. The second one is w, which is equal to -1 plus I, the square root of 3. The third one is zw. The fourth one is the square of z. The fifth one is z over w. So in short, what I'm going to do is we are going just to look at the third one, because the first and the second, these we can handle them as from the previous examples. So now, the first thing is, in one, we are finding the argument and the modulus of z, which is 1 plus I. So in this, after solving, you discover that the modulus is 2, the argument is 45 degrees of pi over 4. Also in the next one, if you look at in the second one, it's the same scenario just as from the previous examples. So the argument of this of W is equal to 2, the modulus of W is equal to 2, and its argument is 120 degrees or 2 pi over 3 radians. Now, you see, we have two scenarios here. So now, here, the modulus of ZW. Now, let's find the modulus of their product. The modulus of their product. If we use the theorem number, that is theorem number 3, using theorem number 3, we are going to discover that the modulus of ZW is just equal to the modulus of Z times the modulus of W, and remember the modulus of Z is 2, the modulus of W is the square root of 2, which will give us 2 times the square root of 2. The argument of the product is, which is the argument of Z times W, according to theorem number 3 again, this is going to give us the argument of Z plus the argument of W, and the argument of Z in radians is pi over 4 plus the argument of W in radians is 2 pi over 3. When you sum this, we are going to get 11 pi over 12. So in all, it's the same. Even if you look at the square of Z, remember the square of Z is the same as Z times Z. So from there, you are going to use the theorem 3, which is above, to answer these counter examples, including in the third one, which involves the quotient of the two complex numbers, where you are finding the modulus of the quotient of the two complex numbers and the argument of the quotient of the two given complex numbers. So then we have this lemma, which is lemma number 5, which is talking about more properties that involves the complex numbers. What we are saying is, for any non-zero complex number Z, which is equal to x plus iy, the square of the modulus of Z, this is equal to the product of Z by its complex conjugate. So the square of the modulus of Z, this is the same as, this is equal to the product of Z by its complex conjugate. And the reciprocal of Z, which is 1 over Z, this is just equal to the quotient of the complex conjugate of Z with respect to the square of the modulus of Z. So the reciprocal of Z is equal to the conjugate of Z divided by the square of the modulus of Z. And the last one is the modulus of the complex conjugate of Z is just equal to the modulus of Z. The proof is given here. The proof is just given here. So if we let this Z being equal to x plus iy, then the first scenario is the square of the modulus of Z, which is equal to the square of the modulus of x plus iy. Now remember, this will give us x squared plus y squared. Sorry, this part was not supposed to be there. So this will give us x squared plus y squared, because this will be the square of the square root of x squared plus y squared, which will give us x squared plus y squared. Now let's also look at Z times its complex conjugate. What we're saying is the left hand side of this equation, which is the square of the modulus of Z, is equal to the square of x plus the square of y. Also, if we multiply Z by its complex conjugate, remember Z is equal to x plus iy, its complex conjugate is equal to x minus iy, which is the difference of two squares, this one, still we are going to get x plus the square of x plus the square of y. So from this scenario, we are able to see that the square of Z, the square of the modulus of Z is equal to the product of Z by its complex conjugate. Similarly, you can also handle part 2 and 3 in using the same scenario. let's look at this lemma. This lemma is a consequence of theorem number 3, is it? Yeah, which talks about the product, the modulus of the product of two complex numbers, which is equal to the product of their moduli, and the modulus of the quotient of two complex numbers, which is equal to the quotient of their moduli. So we just extracted that piece of information and then use it here. So we in this lemma number 6, we are just going to prove part 1. Part 2, you can handle it from the same point of view. So now we need to show that the left hand side is equal to the right hand side. So let's start. Remember, the modulus of z times w, z is equal to x plus iy, and w is equal to u plus w. So this is the same as the modulus of x plus iy multiplied by u plus iv. If we expand whatever is inside this moduli, what you're going to get is xu plus ixv plus iyv minus uyv. If we collect the real parts and the imaginary parts, what you're going to get is the modulus of xu minus yv plus I multiplied by xv plus yu. Now, using the definition of a modulus of a function, the modulus of this is just equal to the square root of the real part, the square root of the square of the real, or the square root of the sum of the square of the real part and the square of the imaginary part. In this scenario, the real part is xu minus yv after the product, after you take the product, and the imaginary part of the product is xv plus yv. If we expand whatever is inside this square root, expanding this xu minus yv squared, what you're going to get is x squared u squared minus 2xy uv plus y squared v squared plus x squared v squared plus 2xy uv plus y squared u squared. After expanding everything, so we are going to get this. Then if we do the collection, now you see we have the negative of 2xy uv and the positive of 2xy uv. So these two are going to cancel. So then when they cancel, you're going to remain with the square root of x squared u squared plus y squared v squared plus x squared v squared plus y squared u squared. Now, when you reach at this stage, then we can rearrange them and then factorize by grouping terms. If we factorize whatever is inside the square root, which is under the square root, we factorize by grouping terms. So what you're going to get is x squared plus y squared times u squared plus x squared plus y squared times v squared. And then we also factor out what is common, whatever is under the square root, we are going to get x squared plus y squared multiplied by u squared plus v squared. Now, according to SADs, the SAD of the product, this is the product of the SAD in short. So this one, the square root of x squared plus y squared multiplied by u squared plus v squared, this is the same as the square root of x squared plus y squared multiplied by the square root of u squared plus v squared. Now, the square root of x squared plus y squared is equal to the modulus of z, and the square root of u squared plus v squared is just the modulus of w. And this gives us the proof, which is part 1 of lemma number 6. Then we are done. In the next piece, part of the proof, we are looking at the triangular inequality of complex numbers, which is lemma number 7. We are looking at the triangular inequality of complex numbers. So we are saying if we have z1 and z2 are any two complex numbers, prove that the modulus of z1 and z2, the modulus of the sum z1 and z2 is less than or equal to the modulus of Z1 plus the modulus of Z2. Secondly, the modulus of the difference of Z1 and Z2, this is greater than or equal to the difference of the modulus of Z1 and Z2. Now, the first one, we call it the triangular inequality. So if you can recall, you did the real number system, you looked at the modulus or the absolute value of a real number, and if you can recall, you did prove something to do with the triangular inequality. So for the first one, I'll just tell you to say refer to the triangular inequality which you did in real analysis on the real number system, on the modulus of the real number on real numbers. The approach is the same. The only difference is where you're at some point you're going to talk of the conjugate, of which if you look at the conjugate of a real number, it's just the real number itself. So it's the same approach. It's the same approach, or you call it the conjugate of a complex number and such things. So the proof though is here, but I can just refer you to look at it from that point of the modulus of a real number. So I'm going to do number 2, which maybe you've never seen. So let's look at part 2. So in short, to prove that this is the case, to prove that the modulus of the difference of Z1 and Z2 is greater than or equal to the modulus, the difference of their moduli, you just from this observe that the modulus of the modulus of Z1, this Z1 is the same as the modulus of Z1 minus Z2 plus Z1. The modulus of Z1 minus Z2 plus Z2, of which there's nothing that you've done here, because the negative of Z2 plus Z2 is 0. Then, by applying the triangular inequality, this is less than or equal to the modulus of Z1 minus Z2, then plus the modulus of Z2. So it's less than or equal to the modulus of Z1 minus Z2 plus the modulus of Z2. Which, what are we saying? We are saying that the modulus of Z1 is less than or equal to the modulus of Z2 minus Z1 plus the modulus of Z2. Simplifying, what do I mean by simplifying? What I mean is, if we subtract both sides by the modulus of Z2, what you're going to get is that the modulus of Z1 minus the modulus of Z2 is less than or equal to the modulus of Z1 minus Z2, which gives us the theorem. And rewriting this, the modulus of Z1 minus Z2 is less than or equal to the modulus of Z1 minus Z2. This is the same as writing, if I start with the modulus of the difference, I'm going to read it to say the modulus of the difference Z1 minus Z2 is greater than or equal to the modulus of Z1 minus the modulus of Z2. So this completes the proof of part 2. In part 3, what you're saying is if in part number 8, if Z1 and Z2 are any two complex numbers, then prove that the sum of the square of the modulus of Z1 plus Z2 and the square of Z1 minus the square of the modulus of Z1 and Z2 is equal to 2 times the square of the modulus of Z1 plus the square of the modulus of Z2. In everything that we do, we are going to take back, we are going to be referring to the triangular inequality. We are going to be referring to the triangular inequality. So now, this is the proof. So we are saying, let Z1 be equal to x1 plus iy1 and Z2 be equal to x2 plus, supposed to be iy2, then the square of the modulus of z1 plus z2, which is equal to the square of the modulus of x1 plus iy1 plus x2 plus iy2, this is equal to, when we collect the like terms, we add the real parts together. Remember, addition of complex numbers, you add the real parts together, you add the imaginary parts together. This will give us the square of the modulus of x1 plus x2 plus iy1 plus y2. This was supposed to be y2 not iy2. From here, you take the square root of the real parts. This will give us the square root of the square of the real part and the square of the imaginary parts. So in this case, because there is this square will cancel with the square root. So we are just going to have the square of x1 plus x2 plus the square of y1 plus y2. This I was not supposed to be there. Next, again, we do the other way around, which is the square of z1 minus z2, which is going to reduce to the square of the square of the modulus of z1 minus z2. When you substitute our z1 and z2, this will reduce to the square of x1 minus x2 plus the square of y1 minus y2. From this now, but then, and also you should note that the square of the modulus of z1 is equal to the square of x1 plus the square of x2, and the square of the modulus of z2 is equal to the square of x2 plus the square of y2. Now from these three parts that you have seen here, then what we do need here, then from left, I'm starting from left hand side. So from the left hand side of this lemma, which is saying as lemma number 8, from the left hand side of this lemma, what we have, which is saying from the left hand side, what we are going to have is the square of the modulus of z1 plus z2 plus the square of the modulus of z1 minus z2. This will give us this. Remember, the square of the modulus of z1 plus z2 is this, which is the square of x1 plus x2 plus the square of y1 plus y2. Which is this one, and also for the square of the modulus of z1 minus z2, which is the square of x1 minus x2 plus the square of y1 minus y2. When we expand these, they'll give us, when we expand all these, they are going to give us this part and also this part. And then after simplifying, when we expand all these terms and then we simplify, we are going to arrive at 2 times the square of x1 plus 2 times the square of x2 plus 2 times the square root of y1 plus 2 times the square of y2. From here, then we are going to arrange them according to the z1 and z2. So rearranging this, we are going to get the square of 2. Remember, 2 is common, so we can factor it out. 2, which, and inside the brackets, we're going to have the square of x1 plus the square of y1 plus the square of x2 plus the square of y2. Now, the square of x1 plus the square of y1 is equal to the square of the modulus of z1, and the square of x2 plus the square of y2 is the one that is given the square of z2, of which is this part piece is equal to the right hand side of that lemma. So then from there, you are done with the construction of the proof. Similarly, example lemma number 9 is the same thing. So if z1 and z2 are any two complex numbers, you prove that the modulus of the difference of the moduli of z1 and z2. So the modulus of the difference of their moduli, this is less than or equal to the modulus of their difference. So the modulus of the difference of their moduli, this is less than or equal to the modulus of their difference. So this one also you can look at it at your own times, but it's the same approach as lemma number 9, lemma number 7, and the other lemmas that you have looked at. So this is the same approach, and the proof is here. it's already done, so you just need to go through it and see the components that you can understand, but the concepts are the same. Even also lemma number 10, the concepts are also the same as in lemma number 9 or lemma number 8. So you can also look at this at your own stipulated time, and then go through it. You'll be able to clearly understand. So what you're going now in general. So this is the end of this lecture number 2, from which we talked about the modulus of a given function and the arguments, and we also looked at the Eigen diagram. So for this lecture, this is the end. So when we meet next time, we are going to look at other components which will involve. We are going to look at things to do with the De Morgan's law, and also we are going to look at issues to do with finding the roots of a given complex number in lecture number. That will be in lecture number 3. So for today's lecture number 2, we are going to end here. We'll meet again next time. Have a lovely afternoon. Thank you for your time.